All right, well, welcome to our new unit. The next section of this chemistry course is going to be about thermochemistry. Now, thermochemistry is the study of heat energy and its relationship with chemical reactions. Chemical reactions can give off heat energy, and they can also absorb heat energy. If they're exothermic reactions, they'll give off heat energy. If they're endothermic reactions, they'll absorb heat energy. So we'll look at a little bit more detail about how that works and the way in which heat energy can be gained and lost, and how we can use that information to learn more about chemical reactions. Because we're chemists, right? We don't care so much about the heat energy part of it. We care about the chemical reaction part of it. So heat energy is going to be a very useful way to learn a lot more information about chemical reactions. And then we can apply that information to various technological processes. So let's remember, first of all, the first two laws of thermodynamics. So the first law of thermodynamics says energy cannot be created or destroyed, only converted from one form to another or transferred from one object to another object. And so that means that if you have a fire, you see heat energy coming off of the fire, right? And you might think that that energy is being created at the fire because, well, the wood wasn't hot. Now the air is hot while the fire is happening. Your hand is hot when you put it close to the fire. But you have to remember that that energy was possessed by the wood before you burned it. It was just in a different form. The wood had chemical potential energy. And then as it's burned, it transfers that chemical potential energy to the air as it converts it to heat energy. And so the first law of thermodynamics especially is going to be very important for this section. Second law of thermodynamics says energy flows from areas of high energy to low energy. And during such an energy transfer, there is always some energy lost. There's no such thing as a perfect energy transfer. That would be a perpetual motion machine. If somebody tried to sell me one of those once, it's impossible. Doesn't work. It's not going to work. And usually this is going to be heat energy is going to be our waste energy form, but not always. Sometimes that's the type of energy that we want. So let's think about a combustion reaction. Okay, if I'm doing a combustion reaction, I'm burning something. So let's say I'm burning the methane in my furnace. And I know that as I burn the methane, it reacts with oxygen, produces carbon dioxide and water vapor. And one of the things that is produced is heat, right? That's the whole point of burning it in my furnace. I want that heat to heat my house. So where does the energy in this fuel come from? Well, the methane is a hydrocarbon. And this hydrocarbon fossil fuel is the chemically changed plant material or plankton material from millions of years ago. So ultimately, the fossil fuel that you're burning in your furnace is actually mostly plant material. And that plant material, it didn't have a lot of heat energy. What it had was chemical potential energy. And that chemical potential energy it obtained by doing photosynthesis. And through photosynthesis, it could convert light energy into chemical potential energy. And well, where did that light energy come from? Well, that light energy comes from the sun. And the sun is, of course, doing a nuclear reaction. And the nuclear reaction is what is the energy released during the nuclear reaction allows the energy in the hydrogen atoms in the sun to be converted into light and then into chemical potential energy and then finally into heat and that you can use to heat your house. So what if we have a jogger? We've got a jogger out for a jog here, working up a sweat, and I've got my jogging headband on here and the wrist, whatever those things are, sweatbands, wrists, because people's wrists sweat a lot apparently. So this runner, he's running. What does he have? What kind of energy? He's got kinetic energy, energy of motion. So that's the kind that he has in the runner, right? Now, where did that come from? So the kinetic energy that the runner has comes from the food that the runner ate. And the food has got chemical potential energy. And so let's say the runner ate a sandwich. That's got lots of different types of nutrients in it probably, but let's pick an easy one. Let's pick the bread and let's focus in on the wheat. And the main ingredient in the bread is wheat, and that wheat comes from a wheat plant, which is doing photosynthesis. And so it's turning light into chemical potential energy. The light's coming from the sun, which is doing a nuclear reaction. So we have nuclear energy before this. And so you see that whether it's your furnace or whether it's you jogging, the ultimate source of the energy in both of those cases is the sun. And for almost all types of energy we see on planet Earth, not all, but almost all, if we trace them back to their ultimate origin, we would get to the sun. And so really, in a roundabout way, your furnace is solar powered, right? The energy that you're burning to heat your house did come from the sun. That's true for the oil that's refined to make gasoline for your car too. That's fossil fuel. So the ultimate source of energy for that is the sun. So really, your car is solar powered too. It's just really ancient solar. So to power your body, we need lots of chemical potential energy. We like to measure energy in joules because we're scientists and that's our metric SI unit. But commonly on packaging, you'll see food measured in calories. Calorie is equal to 4.19 joules. And so if you're a typical person, typical young person, you need between 9 and 12 megajoules of energy every day. And if you're a high performance athlete, you might need 3 times that. You might need up to 29 or 30 megajoules of energy every day because you're outputting so much kinetic energy and you're losing heat in the process that you need to be putting all of that energy into your body. So the chemical potential energy that you obtain from your food, that's stored in the chemical bonds that hold the molecules together. If you have a simple carbohydrate like glucose or fructose, they're a quick source of energy. Here's a glucose molecule. Here's a fructose molecule here. They're a one-ring sugar molecule. They're very easy for your body to break down, so you can quickly use the sugar. So when you down a big gulp Slurpee, right, it's got lots of fructose in it. It's got lots of simple sugars. You can easily break those down and your blood sugar spikes really quickly. Carbohydrates like starch are a lot harder for the body to break down because they're polymers. They're long chains of simple sugars held together by these linking bonds here. And so as a result, in order to use each of these sugars, the first thing that your body has to do is it has to break this sugar molecule off of the chain. And then it can break down the sugar. And because it has to break them down one at a time, it means that it gets access to the sugar a lot more slowly, which means that they're a slower release source of energy. Then in the process of photosynthesis, as we said, we're storing light energy in the chemical bonds of these glucose molecules. And so this is a high energy molecule. And this is an endothermic process because we have energy as a reactant. Energy is going into this, and that energy is being stored in these chemical bonds. So this is an endothermic reaction. Cellular respiration, which on the grand scheme of things is the opposite of photosynthesis, produces energy in the form of this molecule called ATP, which you'll have heard of if you've taken biology. If you haven't, don't worry about it. But we produce high energy molecules in cellular respiration. That energy is a product, which means that this is an exothermic reaction. And that's because we're taking this high energy glucose molecule and we're breaking it down. And as we break it into smaller molecules, carbon dioxide and water, as we break it down into smaller molecules, we release that energy. And when we release that energy, then it can be used for other things in the body. So you can kind of think of the glucose molecule like an energy battery. In photosynthesis, we charge the energy battery by building the molecule, right? And that stores the chemical potential energy. And then in cellular respiration, we break the molecule apart and that releases the energy again. And it's a rechargeable battery. You can take those same carbon and oxygen and hydrogen atoms and put them back together again. You can pull them back apart again. You can put them back together again. You can pull them back apart again. And you can keep doing that over and over and over and over and over again. And those atoms just keep getting recycled. And that's the reason why in the air that you're breathing in right now, there are oxygen and carbon dioxide molecules that were metabolized by dinosaurs or by famous, historical figures like Aristotle or something like that, because they keep getting recycled over and over again.